All right, so the next part would be rectifiers. This one, I need to go there. Yeah. So what is a rectifier? It is another type of converter which convert AC power to DC power. For the symbol, sometimes you see that they use this kind of symbol, right? So this is AC side. This one is bridge, switch. Yeah, switch components used for bridge, and then you have the DC side. Or sometimes you just see block diagram like this, representing you have AC from the left and then DC to the right. First, let's see a half wave rectifier. It's called half because the waveform of the output is just half sine wave. So look at here, you have a voltage source as a sine wave, and you have two diodes to be like this. So let's do a quick analysis. When sine wave is positive, this diode D1 turn on, this one turn off, and then you have voltage at VH here. So VH here means the terminal around here and here. So VH would be equal to this when D2 is off, right? So that's why during the positive voltage of the source, VH is the same as source. Then when the source is negative, this diode is off and this diode is on, just free running like this, similar to what you seen earlier, I mean in the example. So when this one is on, this two is on, you got VH just short, so voltage VH is 0. Okay, and then it repeats. Then because VH is the source for the DC side, right? This is DC side, and VH would be the source for DC side. Then we can find the voltage, average voltage on the load to be the same as average voltage of VH. Why? Why is that? Average voltage of the load here the same as average voltage of VH, because average voltage of inductor is 0. Then you can compute using average value formulation using the integral over a period, and then you can find average voltage of VH is just Vs over pi. And yeah, for big inductance, then the current go through the load would be constant, to assume to be constant. Yeah, actually it's almost constant. You choose very large LD. Right. Next, you can see full wave rectifier. Yeah, full wave rectifier, you need to use 4 diodes in order to have full wave like this. So you look at the waveform of VH. Actually, it's just absolute value of the waveform of the source, because the source can have positive voltage and negative voltage, but after it passed through the bridge, VH here, it's just absolute value of the sine wave, right? And this VH is the source for the DC side. And actually, sometimes you can see the schematic for full wave rectifier to be like this or to be like this. They are the same, right? Let's say I take this one out to here, like this one. Take this one out here. This terminal still keep here. This terminal still keep here. So it just same. Then if you compare this to the block diagram or schematic, you can say that this one to be more abstract, so in this case you say block diagram. AC side to be representing this, and then the bridge here to be representing this, right? And this DC represent this part. All right, and then again you find the average value of VH because it's gonna be the same as average value of the load. So you take the integral over a period, because this full wave, for the half wave the average value is Vs over pi, then the full wave must be 2 Vs over pi. Okay, here you see half wave, and then here full wave. Yeah.
Can you explain more about when
Okay.
T is when I is positive and I is negative?
All right, it's not I, but V. Yeah, right. Yeah, I forgot this part actually. Okay, so let's say you use this plus terminal and this minus terminal. If current flow out of the plus terminal from the source, we say I here is positive. Okay, so because this diode cannot allow it to flow backward like this, then it goes this way, and then it can't go this way, right? Because this one block as well, so it go here. So you see that this is from top to bottom, and come back here because the voltage, the current across resistance here, then it drop voltage a little bit here. When it drop, it can't go the same way because this one is higher, so it must go this way to back to the source. And when the sine wave is negative, the current flow this way, right? It go out of the negative terminal. When it go this way, this diode cannot allow it to flow, so it go this way. Go this way, and again you see that is one from top to bottom, and so it drop voltage a little bit, so it won't go this way, but it go this way. Okay, so you see that here is alternative back and forth, but here you only see one direction from top to bottom, so it's DC. Is that you want to know?
Yeah, why it can go through D2, why not D4?
Which one? The green one or the red one?
The blue one.
The blue, sorry, no green. The blue one. What you say? Why not go through the 4?
Yes.
Huh? What do you want to say? Well, when they go up here, actually this one want to come here, but this one block. Okay. This one is higher, right? This one is high potential. This one is lower because already passed through a resistor. So this one is low voltage, low. So I use this notation to be low, and here to be high. So this one push to this way, not this one push up like this. Okay. Right. And then next about load regulation. So in practice, when you use rectifier for your device, it might be affected by other user, other power consumer. If they use large motor around us, or sometimes the transformer has magnetic leakage, then there is effect of so-called parasitic inductive load from the AC side. This is still AC side, and let's say your device that you are using with your, just example, with your computer or Okay, in my case, I'm using it, right? Yeah, because that one convert from AC to DC. So this is your device that you are using, right? This is from the electrical socket from the ITC-DCLab board. Okay, so or maybe other power consumer use large motor which has inductive load, then it can affect your system. Now we can let's analyze how it can affect your system. Let's assume that the inductor at the load of your device is large enough so that the current flow through here is constant. Okay, then we assume that you have current source here as ID because it's always constant, right? So the influence is that when this one change from negative to positive, because this is sine wave, right? Sine wave. When it change from negative to positive around here, this one does not need to be zero. Maybe I draw here. Yeah, when it change from negative to positive, the current that pass through inductor here cannot immediately go up to the maximum, because this one, like you learned before, that if you want to avoid the jump of current, right, then you use inductor. That one is for useful use. That case is useful, but this case is not useful. Actually, we want current to be as high as possible, I mean in a short time. Why is that? Because in order to fulfill the current needs here as ID, you want current from here as ID as soon as possible. But if you have inductor here, the current just go up slowly, like this before it reach ID. Just go like this, right? So it means, how can you get ID here? It means current must flow through D2 a little bit, right? Because I1 is less than ID. Then because I1 plus I2 has to be equal to ID, then it means I2 has to be positive, which means D2 has to be on, must be on actually. D2 must be on, then it means during this period of time, VH is still zero. If VH is still zero, it means you don't get power to your load. So what happened with the waveform? So I'm not going to explain every detail on the calculation here. What happened? So here during the transition, when I1 increase up to ID, VH is still zero. So now we can see that the average voltage of VH compared to the ideal case, VH has this waveform, right? So between the black one and the blue one, which one has higher average value? You compare the black one, the solid, the black and the blue here that I just draw here. Which one has higher average value?
Black one.
Not this black, but this black. You see, a rear under the curve of the blue one is higher, right? Here, the rear under the curve of the blue one is higher than under the black. I mean this black. No need to say this is black because it's just the same, right? Except it has negative part here. So it lost this area. We lost this area. So it means the average value of VH in this case is lower. And if we look at the equation, average voltage of VH equal to, in the ideal case only Vs over pi, but now Vs over pi times 1 minus something. 1 minus something, so which means this one is less than 1. That makes average value of VH less than Vs over pi, which is the ideal case. So so here there is a mistake here. Actually, there's no this 2. So you can see that because this average value of VH is in function of ID also. ID as current at the load that we want to operate. So the higher the value of ID you want to operate, the lower the average voltage of the VH. Don't forget, average value of VH is the source for the DC side. So if you got lower voltage of VH, it means you may have low power. So actually, if you use too high ID current at the load, you got very low power. For example, at this, let's say you operate ID at this zone. Okay, so you get a voltage just around here, and then the power that you can draw from the source actually only this, right? Current times voltage is power. So not so big power, but the base operation to get the highest power is at the middle here. And you know this one and you know this one, then you want to get the highest power, you must operate around here. Okay, so anyway, in summary, when there is LC side, LC inductor at the AC side, then your rectifier can be affected. I mean, it can draw less power. This is the final conclusion. Same thing for full wave rectifier. You can get a similar graph, but here because average voltage of VH, if you don't operate any current at all, voltage VH can be up to 2 Vs over pi. Okay, but then if you operate with the current of this value, then you don't get any voltage from the VH at all, right? Okay. Any question? No, so then I go next. This one, single phase diode bridge. Yeah, this one just has more calculation, more detailed calculation. Okay, so next we consider power factor of a rectifier. Yeah. So the formulation of power factor is the real power over apparent power. Once you know waveform of current and voltage, you can calculate root mean square value respectively. So here I don't explain the detail because you already learned the process how to find power factor. So here you just can notice that the power factor of a rectifier is only 73%. Okay, for full wave rectifier. So what does this say? What does it mean, 70% of power factor? So let me ask, power factor and efficiency is the same thing or not? Can you say power factor and efficiency are the same terms or not? Right, no. Efficiency means the power of the output that you get is less than the power from the input. Okay, The power factor means the power that you can receive at the output is less than the input, but the remaining is not lost. It just to store somewhere. It just store somewhere. But for efficiency, the remaining part just lost. Okay? Because if the power stored somewhere, it's gonna return. It's gonna return. So in terms of energy, you don't lose anything for power factor. But in terms of power, you cannot use the maximum power that the source can give. Just like that. Yeah, you can say, yeah, so it's easy to distinguish when you talked about energy, yeah. You can find the difference between power factor and efficiency. And here is single phase thyristor bridge, also full wave, but and here we have more control on the system. For the bridge that use diode, we cannot control it all, right? The circuit itself force it to turn on or turn off. But for thyristor, we can send the signal to the gate of the thyristor to turn it on, but we cannot command it to turn it off. Okay. So the way we do to turn two thyristor on is to send the signal to, for example, we want to turn thyristor 1 and thyristor 3 on at the same time. So we just use only one signal but send to the gate of both thyristor. And then if we want this one to be off, because we cannot control it to be out, we just send the signal to turn on thyristor 4 and thyristor 2. So when these two are on, these two are automatically off, because the circuit will force these two to be off, right? So that's why here we can have waveform like this. If we fire the pulse to turn on thyristor at angle alpha, so here is alpha and then here is pi plus alpha. We fire the angle alpha to turn on, for example, TH1 and TH3, and at the angle of pi plus alpha, we fire pulse to turn on TH4 and TH2. Okay, in that way we can have a periodic waveform at the here. We can call it VH like before, VH here. Okay, so here is VH, which is the source of the DC side. Okay. Yeah, DC side to this way. Then we can compute the average voltage over a period. Just take this from alpha to pi plus alpha as a period, see? And the waveform is just a sine wave. Then we can have average voltage. And power factor can be computed to be, it looks similar to the previous, here. So the amplitude of this cosine alpha is the same as power factor in the previous case, for the diode's case. But now we have the term cosine alpha, which means if you fire alpha at 90 degrees, you get 0 power factor. You don't get any power transfer to the load at all. If you fire alpha as larger than 90 degrees, it's like you got a negative power factor. It's kind of like you draw the power back from the DC side to AC side. Yeah, it's in that sense. Okay. Let's say if DC side has a constant voltage, right? And if you switch this way, it's like you are trying to draw power from the DC to AC. Actually, this is also the initial concept to inverter, because inverter you convert from DC to AC. And the last part of the rectifier is the combined bridge, which means we combine between thyristor and diode. So what is good for this? This is good because yes, in some application you never want the voltage from a VH to be negative. You never want that in some case. So you must use this combined bridge because there's no any part to be on the negative side. When you find average value, you never get any negative voltage, right? For this case, you are low to have negative voltage. Okay. And the power factor can be computed to be like this. And if we compare the two cases, thyristor bridge and combined bridge, and we find that the power factor of the combined bridge is always larger than that of thyristor bridge. Yeah, we already finished for rectifier of single phase. Yeah, I said the last part. When I said last part, I mean last part for single phase. Now let's see the three phase rectifiers. Okay, so for three phase, from the source, actually you have three wire, 1, 2, 3. 1, 2, 3 has sine wave in this way. The red one, you can see here, the red one has equation Vs sine omega t, and the blue one has equation Vs sine omega t minus 120 degree. But in writing, I prefer write in radian because when you program, you always use radian actually. So just have it. But when I say 120 degree. Okay. For the V3, the green one, yeah, it has equation like this: sine omega t plus 120 degree. How do we know that? Yeah, how do we know that? Yeah, for this one, minus 20, which means when omega t equal to 120, sine of 0, you got 0. So actually here is 120 degree. Okay. 30, 60, 90, 120. So each grid represents 30 degree. Each grid on the horizontal axis. And then when two wire, when we compare between two wire like 1 and 2, then what the waveform look like? Let's say we compare the two, but let's say we don't use any switch, any diode. What waveform it should look like? So we compare the two, which means we subtract between this waveform and this waveform. Okay, V1 minus V2, so sine omega t minus this sine, you compute it. In the graph, you can represent it by the gap. So look between the red and the blue. You see that the gap here is the maximum. That's why here the red here is U12, which means V1 minus V2. That's why you see it maximum around here, and it's 0 here because V1 equal to V2. So you see the red here is 0, right? And the gap around here is just small like this. Okay, so V1 minus V2, you got this one. V1 minus V3, you got the blue one. V2 minus V3, you get the magenta one. And V3 minus V2, you get the light blue. Okay, just call it light blue. This okay. And so then when you you use bridge or you use diode, it means you cannot allow negative voltage, right? No, what I'm trying to say here is that the one that is higher, the one that has higher voltage will survive. I mean, how can I say this? Because if this wire has voltage less than this wire, then this one turn on to be like this, right? This one to be on compared to this one. So the waveform for this, I mean out of the bridge would be only the top part like this, right? Because only the highest voltage will go through the diode and the current flow this way. This is the idea. It's very hard to explain this phenomenon actually. So yeah, I try my best. So if you have more questions, then please ask. Yeah, well, we compare. Yeah, because these two, the comparison between these two is here. Only the highest part of these two would pass through here, right? And between this and this would be here. Okay. So that's why only the highest part pass through the bridge like this. So the voltage VH here would have the waveform like this. Okay. Yeah, VH itself almost straight already. When we have inductive load, then average value is even more. Yeah, would be here, and the higher inductor we use, the more straight the waveform at the load, right? So at the maximum VC mean the voltage here. Yeah, because the average value of VC here is the same average value of VH here. So the maximum is square root of 6 times V root mean square. Vs root mean square. What is Vs root mean square? Vs root mean square because you see that the waveform, the original waveform is like this. So it's just Vs over square root of 2. Okay? And VC mean, yeah, it means to be this value here. And then the mean value, which is between here, between the mark and the mean, so it's around here. Yeah, this one. Okay. And then for thyristor, because for the thyristor we can control, we can fire pulse to turn on and off. No, sorry, to turn on particular thyristor. And there is certain sequence that you can turn on thyristors so that the waveform of VH out of the bridge would be like this. So why we want that? Because if we use diode, we only have fixed average voltage of VH. But in some case, especially when you build amplifier, power supply, when you build power supply, sometimes you want to change the voltage to be this amount, that amount, right? So thyristor would be useful in that case. And the difference between the average value of output is different from that of the previous case, and the difference is only the term cosine alpha, right? So if you fire alpha 0, it means you have the same voltage of the output as the previous case. Yeah, we still have 30 minutes. So any question for this part before I go to the remaining part? No question? Busrong, you want to ask something? Huh?
So the voltage output is still waveform.
Yeah, around. Yeah, and here we say inductive load, but in practice, at this brand actually you have the best way to have DC side is to use one inductor and then one capacitor like this. Yeah. For this, okay. So this is just a simplified version of this. Okay. So voltage VH here is supposed to be, yeah, VH should be like this. I would say must be like this, not should be. Must be, yeah, if we fire at a certain pattern on the thyristor, VH has pattern like this, okay? But the voltage in here, would be just constant, which is the average value of this waveform. Because this one and this one would have maintain a voltage to be as straight as possible. We can say inductor try to regulate the current to be straight, and voltage try to regulate the voltage, right? But in some practice, for rectifier, people don't use inductor at all, just use very large capacitor. Because they use when we use diode, it doesn't matter because there's no switching. For thyristor, it's combined between diode and MOSFET. Right? If you use MOSFET and if you use only capacitor, it can destroy MOSFET. The destructive circuit you have learned before actually. If you don't use this one, you only have this, you might have destructive circuit. So the best way is to use both inductor and capacitor to protect all components. All right. So the last part will be inverter. So inverter is opposite from rectifier because it's convert from DC to AC. So like here you can see in this block diagram you have DC side but denoted by E. You have two source, one is plus, one is minus, like this, and then you got load like this. This is a single phase and only half bridge. Look, wait. Oh no, okay. We don't call half or yeah. This one is just half bridge. So look how this function to be an inverter. You look at the switch K1 and K2. These two work commutatively. I mean, one is on and another one must be out. Why? Because if you accidentally turn on both of them at the same time, you got a short circuit. Okay. So look, when you turn on K1 and turn off K2, then you have only current flow this way. So look at the load, you can see that from if I say this is positive terminal and this is negative terminal, then you see that the current flow from plus to minus. And next, if you turn on K2 and turn off K1, then you get the current to flow this way. Right? So it flows through minus to plus terminal. So you can see that current can flow both direction on the load, which means AC, alternative current, right? This is the most simple inverter. Okay. And to implement the switch for K1 and K2, we can use transistor and diode like this. To have a filter, in order to make the waveform to be not square like this, because AC we prefer the waveform and the AC to be sine wave, right? We prefer AC to be sine wave like this. So we use filter element. So like inductor, okay? Inductor in series with the load, and capacitor in parallel with the load. Just same as previous, same as the load that we use with rectifier. Yeah, we call RC filter in this case. Any question? Okay, then I go next. Okay, so here is inverter with L filter, only inductor. And then the switch function we apply for the switch to be on and off in this way, so that we can have voltage across the terminal here, U, to be like this, and then the current I. So if we switch very fast, or we use very large L, then the waveform would be like this. The waveform of the current would be like this, because for this one is just first order. The first order, the transient for the current to be like this. If you keep this one constant, I mean voltage constant, the transient to be like this. But because you switch the voltage to be the negative part like this, then it transit from here to here like this, right? So you don't have steady state of, I mean, look, if we have the step of voltage like this, then the current would go like this, which has transient part and then steady state part like this, right? This one is called steady state. But now you switch the voltage U to be like this, so it would change. It cannot reach steady state for a constant voltage. You got what I want to say? The response of the current cannot reach steady state for the constant voltage, because the constant voltage is not long enough for the current to reach steady state. So when voltage change, then the current change again, then it always stay the transient, right? But because it repeat over time, the shape of transient here look like a transient here, right? This shape repeat over time, then you got a periodic steady state. Yeah, it becomes just periodic steady state. You got the point what I'm trying to say? Yeah, but what I'm trying to say is like the if I yeah, you have seen periodic steady state before, right? I explain in this way, not really this one, but I explain this way. It's let's say you see this one like a transient of the switching, right? Transient of the switching. But if you look carefully, during this part, it's not periodic steady state. But during this part, it is periodic steady state. Right? But if you look detail on this part and this part, actually it's just transient of the response for the constant voltage. Because constant for a period, okay, constant for a period, and then it fall to a different constant like this. Yeah, if you understand these two concepts very well, you can easily draw the response. So here full wave inverter. So for full wave we have 4 switch. Okay. So here we implement in this case when you look at this, this is called opto transistor. So it's just another type of transistor. Sometimes we need to use opto transistor because we want to separate the high voltage, high current on the circuit from the gate, the signal of the gate that we control. Okay, we want to separate, no ground together, no at all. It's completely isolate from each other. What are the difference between this and this? So in this case, we control on the switch 2 by 2. Okay. So the difference is that in this case we only need one DC source. For this case, we need DC source. We need 2 DC sources. Okay. And the waveform look just the same. The difference is that Yeah, okay, so the waveform is just the same. We have plus E and minus E, and the good thing is that we just only need one source. And this is a different way of controlling the switch. You use a different type of switch function, like for example like this, to have some off period. So the waveform like this. Actually, with this waveform, when you use filter, it more or less look like a sine wave. I mean, better like a sine wave, right? When we use filter, that's why this is useful. This one, yeah, this one might have a phase shift of sine wave. Yeah, this one it's better. Okay, because the extra amount of power here would compensate around here, right? And the extra amount here would compensate around here. The next one, three-phase inverter. So here is a DC side, and we have the bridge, and then the AC side would be here from, this is C, right? C connect to C here, B connect to B here, and A connect to A here. Okay. A, B, C, yeah, like this. So this can represent a schematic for controlling a three-phase AC motor. Let's say we have DC power source, but we want to control AC motor, three-phase AC motor. Then we need inverter. Okay. So we can apply switching function on K1 up to 6 such that we can have voltage at terminal A, B, C. So this one A with respect to N is here. A with respect to N, it's more or less a sine wave. Okay. Before it go through filter, it looks like the stair like this, right? So here is VAN, VBN, and VCN is similar. It just we need to have the phase shift of 120 degree from A to B 120 degree, from B to C 120 degree, and then from C to A also 120 degree. Yeah, or you can say from A to B you minus 120 degree, and then from A to C you plus 120 degree, like this. So if A is sine omega t, B is sine omega t plus or minus 120 degree. Okay, like this. Make it better. So right here. Okay, and this one, yeah, we have amplitude, just call it A, amplitude. Oh, look, wait, just call it V, B, this one, just call it V, sine omega t, this one plus, okay. Okay, the next part is about PWM technology, pulse width modulation. So how can we define the switch on and off of K1, 2, 3 up to 6? So we switch them on and off based on we switch them on and off to implement pulse width modulation. Pulse width means the period of the switch on, right? Pulse width, the period of switch on, as is a fraction of the whole period for the complete pulse on and off. So in order to do that, we do comparison between the sine wave and triangle signal like this. So actually this the triangle is at very high frequency usually. This one can be up to 20 kilohertz, and this sine wave is the usual 50 hertz. Yeah, let's say we want 50 hertz to control AC motor that is operated at constant speed. We don't want to change the speed of the motor, like a motor for the drilling, okay, drilling machine, it's AC motor. But big drilling, because big drilling use 3 phase. A small one does not use 3 phase. Okay. Anyway, what I want to say is the frequency range for the sine wave form is small, but the frequency range for the triangle signal for PWM technology is high. And then when we do comparison, let's call this one is 1, this one is 2. Which one is 2? Sorry, maybe this one is 2 and this one is 3. Okay, so 1 compared to the triangle, it's higher than triangle because triangle is low like this. So it's higher, then it's switch on. And then 1 here, from here to here, it's lower than triangle, and then we switch off. And then it's higher triangle again. From here to here, you switch on again. See? And same for 2 and 3. Let's see 2. 2 from here to here, it's lower than here to here, lower than triangle, so it's switch off. And then from here to here, it's higher than triangle, then switch on. From here to here, lower than triangle again, so switch off. See? So in this way we can implement the switching for K1 to 3. And but to be precise, actually, if the waveform is on this K2, but then this one is K2 prime. Okay, or when the triangle is, when the triangle is on the positive side, we use K prime. When the triangle is on negative part, we use K. Actually there are 6 switches here only to illustrate 3 switch. To have the full, you need to find the table. So I don't have the table here. The table of the switch function. Okay. Then let's look at application for application of inverter for controlling a motor. So in practice, we have power source as AC, which is fixed AC with root mean square value as 220 volts for each line. Okay, this line 220, this line 220, this one also 220. And when it pass through the diode, this part is rectifier, right? This part, this part rectifier. And then this part is inverter. Okay. What about this part? Why do we need this part? Can anyone give any idea? You see the term variator de vitesse. What does it mean? Yeah, change velocity, right? Change speed of this. We want to change the speed. If we don't have this term, we got the voltage from the source, but three phase, not this one single phase. And then we got fixed DC voltage. After that, we change it into AC, but at different frequency, for example. Right? Sometimes we want to change frequency, also change the amplitude. So actually, this part is to change the amplitude. Right? Okay. So this part we can say we use it to change the level of DC, because when we got the DC from the rectifier, it's fixed. But if we want to change the DC, then we use the switching technology on this, right? So just control on the duty cycle to get the average value of the DC, and then we implement this inverter, so we can control frequency. Okay. So when we change the frequency, then we can change the speed of the motor. Yeah, of course it depends on different type of motor. There are many type of motor. Some motor are synchronous. So it means the frequency of the motor, of the speed of the motor is synchronized with the frequency of the sine wave that supply to the motor. Okay. So we control the motor by just controlling the frequency of the signal that we supply to the motor. So let's see one common application. Let's say let's say we want to have a backup system, for example UPS. Like in Cambodia, sometimes we have blackout. So let's say you're running a computer server that you don't want to be, you need to maintain the power supply all the time. So when the grid is blackout, then you need a backup from UPS, from battery. So the battery is DC, but your computer server need AC, so you need to use inverter. And also if you use in factory, some factory use a 3-phase motor to operate production line, and they don't want it to disconnect, and they want to use a backup, something like that. Also energy generation from wind power. Actually for the wind power we use many things, many power electronic component, right? If you look at this one, can you recognize this? So from here you have generator that generate AC, but because the wind speed can be slow or fast, then this generator can generate the signal, the AC signal at varying frequency, sometimes fast, sometimes slow. So you convert into DC first, and then you invert DC to AC at the specific frequency, right? And this one is it use for brake. Sometimes you limit the maximum speed for maximum speed of this, such that it's not going to destroy the generator or something. Okay. All right. Any question? Yeah, and another example, like we have solar power. Solar power is DC, but sometimes that DC is not suitable for the battery. It's not suitable for charging battery. Then we need to use boost or buck in order to convert to the right amount of voltage that we can charge to battery. Okay. And let's say we want to use the power for AC motor. So because solar is DC, then we need to use inverter, right, to convert from DC to AC. So it's like you have all kind of converter for a solar system when you want to use it with the motor that, for example, solar pumping. So use solar, and then you want to use AC motor to pump water. Okay. You even have a charge controller. Charge controller is another type of power electronics component, device. Sorry, not component. Okay, so that's all for lecture today. You have any question? I can take one or two. And yeah, if not, I finish now.